why we have to do it. Left is short. All right. I still want to go through that really quick, really quick. Okay. So time constant for capacitor is what? You just have to memorize it. I'm sorry, since I already derived it for you. So you just have to tell me. Cannot do it over and over again, right? RC, right? Inductors, L over R. Okay? So these could be potential. Oh, I already got exam 2. And I was looking at exam 2. So you just have to know these, right? In order to get a good score on that. Fundamentals. It won't be as difficult as the problems in the homework, but these are fundamentals, you just have to know. So what's the natural response equation? You just have to know. Just have to know it. What is it? So if I got a capacitor discharging through a resistor, it has a VC0 on it at the very beginning, stored in there. So at T0, you close the switch, you start discharging to the resistor. And that VCT over time, the voltage across the capacitor over time, will be what? The initial voltage times the attenuation factor, right? That's the very first example you just have to know. We spent the entire last week to let you guys learn it. If you couldn't remember the step responses, you just have to know this at least. All right? Same to inductors. What about inductors? You close the switch, you discharge it. There was an initial current in it. It's IL, what? Initial current is IL what? 0. It's naming convention, right? So what is ILT? Same thing. It's just IL0 times what? E minus T over the time constant, which is L over R. So that's why sometimes you see people directly flip it to the top. It's getting IL0 times what? E minus RLT. But that makes sense, the same thing, right? Natural response for capacitors and inductor. You just have to know this. This will be on the Friday in-class practice. And I'll look at the exam 2 problems and extract the main information from there and let you practice on Friday, okay? But you have to know this. What about step response? Can you help me draw the schematic of the step response? How do you want to model it in circuits? What's happening? So this one is very simple, right? Just draw an initial component with the initial voltage or current in there, and then close the switch to discharge it. That's called natural response. For step response or forced response, what the circuits should include.
You should have an infinite power source like a power plant forcing it to do something else than just natural discharge.
Is this enough? This is V what? VC final, right? This is what? VC what? VCT, but there's the initial what? VC what? Okay? This is the model, okay? Can you draw it by yourself? Think about it. You should be able to do that, okay? Close the switch. This is called step response. It's forced response. The full model has initial voltage stored in there. And then you close the switch, it's forcing this one initially after 100 years. It's gonna force it to be this voltage. So that's why it's called a VC infinity. Because that becomes the final voltage. You close the switch, at the very beginning there will be current. Charging it up, after it's fully charged, no current anymore. They have the same voltage. Make sense? Okay. Got a resistor here. So, what's the equation determining VCT? What's the equation for VCT? VC infinity plus VC0 minus VC infinity times e to the power of t minus t over the time constant, right? Okay? And there are two special cases. The first one is what? If VC0 is 0, so which means there wasn't a initial voltage stored in the cap, what's going to happen? It just changes to 0, right? And the equation becomes what? VCT becomes what? This is just something you have to remember. It's 1 minus e to the minus t over RC, right? Okay? If VC infinity is 0, what's going to happen? What is it?
Step response.
Close. If this guy is 0,
Natural response.
yes, you are trying to force it to what? Ground. Which means, AKA, you have nothing here. You have nothing here to force to anywhere. It's basically discharging it. Right? Make sense? If you got a wire here, look at it, close the switch, initial voltage, discharging through R. What's the difference? No difference. It becomes a natural response. What's the equation? VCT equals what? Natural response. Natural response. What is it? What is it? Yeah, VC0, right? Times e to the negative t over RC, right? Repeated it for so many times. Natural response. Same for very similar cases for inductors. Response, it just changed the voltage current and changed the time constant. So for ILT equals what? IL infinity plus IL 0 minus IL infinity times E minus T over L over R, right? Okay. Now it's ready to move forward with the problems in homework A. Okay? Here's a circuit. Two ohms, a millihenry. It's T0, it opens it. 6 ohms, 30 ohms, 3 ohms. The voltage is 150 volts. The first question is initial value of I. Initial value of I. Part A, okay? So where's I? I is here. I, current going up through the inductor. What's the initial value? So before T0, the switch was closed for a long time. So what the circuit looks like when this is closed. Okay, DC, right? What is this? Wire. Okay? No current change, which means IL di dt, VL is L di dt, no current change. It's been there for 100 years. So what is V over cross it? No current change. Di dt is the current change. No current change. What is the V across it? 0. It's a wire. No drop. What's the current? It's a week 1 problem in circuit 1. Any question on this? How to get a current here? Can you get a resistance over here? 6 times 30 over what? 36, which is 180 over 36 is what? 5. So it's 5 ohms here. That's 3 ohms. So what's the voltage here though? Vx. Vx what? 150 times what? 2 resistors in series. And voltage divider problem. 5 volts over here. This is ground. So Vx is basically the voltage across a 5 ohm resistor. Voltage divider equation. 5 over 3 plus 5. Which is what? I'll let you calculate it. So if you got a Vx, can you get the current here? Yes. Ohm's law. Any question on this before we move forward? Easy, right? Okay? Energy. Initial energy stored in the inductor. What's the energy equation? You use it omega 0, whatever. You can use E if you want. Okay? Which is a half L I squared, right? So that's the initial current. You got a current, that's the initial current. And use this equation to calculate it. This is easy. What about time constant? Time constant for T. Let me write it down. PC. Time constant for T larger than 0. T larger than 0, what does that mean? T past 0, which means it's right open, right? It's right open. So is this guy storing a initial current in there? Keep in mind, I'll repeat it in the future. So inductors, L can't change current instantaneously. See, I can spell it. So inductors cannot change the current instantaneously. What does that mean? So before T0, it was closed and it's running a current through it. And at the moment, at T0, you open it. So the current here is not changing at that moment. Keep that in mind. Super important to solve the equations. All right. Initial current flowing in it. You open it. It's not, the current is not changing immediately. It's still that. So T IL 0 minus equals IL 0 plus. Even though you open it at T0, at 0 plus, the current is not changing. Keep that in mind. So in that case, if you open it, this guy still has that current, whatever it had, and then it's going to start discharging to the resistor. Start discharging. Starting with the initial current, the biggest one, then discharging through the resistor. So this is open. You only have this circuit on the right hand side left, because this is all totally disconnected from the circuit. So this is gonna loop through the resistor and loop back to the inductor itself. What is the time constant for this circuit? What's the time constant? What's the time constant of the RL circuit? L over R, right? L over R. So what's the L? 8 millihenry. What's R? 2 ohms. So what is it? 4 millisecond. That's how I calculate time constant. This is the easiest version you guys are going to see. So later on, there will be a resistor network to let you find out the Thevenin's equivalent resistor for that time constant. But you should be able to do that. We'll go through that. Okay. Police department. I0t equals I1 plus I2 times E minus over tau. So tau is a time constant, okay? What is I1? What is I2? What is I1? What is I2? So I0t is actually ILT, I think. What is that I1? What is I2? What kind of response it has over here? What's the response? What type of response? You open the switch. What is the response here? What type of response it is? Natural, right? It just simply discharges through the resistor. It's natural response. So if you look at this thing, does it make sense? Do you need this guy at all? No. So what is this? I1. 0. What is this guy? What's this guy here for natural response? That's IL0 minus, right? That's the initial current flowing through that inductor right before you make the change. We did it so many times at the very beginning of the class, right? For natural response, you have the beginning or initial current for the inductor and voltage for the capacitor, and then times that attenuation factor here, right? That's the natural response. So do you know this current? Do you know this current? Definitely. It was closed. Looks like this, right? That's how we calculate it. You can find out the current here. Make sense? Okay. Percentage of initial energy stored has been dissipated in the 2 ohm resistor 3 milliseconds after it opens. So which means at t equals 3 milliseconds, percentage of initial energy dissipated to the 2 ohm resistor. So after 3 milliseconds, right, since we know this is a natural response, it's going to discharge through it. So losing energy, dissipating energy to the resistor. So after a while, after 3 milliseconds, how much has been dissipated? So just need to find out E at 3 milliseconds. Initial E minus this, right? This is the energy dissipated. And this is the total initial E. You got initial E there. Right after you open the switch, right? There's initial current, so that's the maximum current you have, which is able to find out this one, and minus the energy it has at this T, right? What's the initial? What's E0? What is it? It's just a half times L times IL0 square, right? What is E 3 milliseconds though? You need to know. Oh, so E at 3 milliseconds is a half times L times IL 3 milliseconds. Do you know ILT so we can plug in this number in it? Do you know ILT? Yes, we have calculated, right? We know the time constant. IL0 times what? E to the, square, sorry. L over R. So this T should be replaced by 3 milliseconds. That's it. Plug in. Boom. Boom. Boom.
Is there a reason we don't just write it as e to the negative tr over l? I mean, it's the same.
Oh, yeah, definitely, yeah. I just want
Just
to,
like proper form to do like that? Or?
either way. Actually, R over L is more common because it looks better. But the thing is, at the very beginning, I just want to show you this is a time constant, right? Time constant.
Oh, just, yeah, usually it's in L or something.
Yeah, it's the minus t over the time constant. Okay? That's all the questions for the first problem. And another example, I'm gonna show you. Do you want me to work on different problems or the homework problems as examples? Do you want me to find out Google different problems or this is better? These are just examples, right? Okay. Since we don't have time to do more things, right? Just directly find out the most efficient way to teach. So I'm not lazy, right? It's not because I'm lazy. Sometimes lazy is better. 50 millihenry IL 200 100 300 50 25. Oh, there's I0 here. It says has been open for a long time. So you can see the direction of the arrow here. Actually, you can tell. So before T0, it was open. So T0 is swing. It was switched down, switched to here. So it's close it. So there are a bunch of questions. This is a really good problem, actually. So let me list all the parameters for you. See if you can get everything right. Okay. This is a good one. Really good one. So IL. Oh, here's IL. Here's I0. Okay, cool. What is I00 minus? What is it? 0 minus means what? There's only like a 1 nanometer between this switch and this connector, right? It's 1 nanometer distance, but not touching. Right before it touches. So still disconnected. Yeah, 0. 0 what? Amps, okay? What about IL0 minus? IL. 0 minus means this is disconnected. And what is this? It's been there for 100 years. What is this? It's a wire, yeah. So can I get a current here? So that current is what? IL what? 0 minus, okay? So circuit looks like, I'm not directly giving you the answer, but I'll draw the circuit for you. So when you are watching the video, you'll know what's going on here, okay? So here's the IL0 minus. 200, 100, 300, 50, 25. Not difficult to find it, right? Okay. What about I's? But how to find it, just in case. How to find it? It's the same problem as the one we just talked about, right? This is the combined resistor. Combined resistor, find out the equivalent resistor, can get here Vx, find out the voltage here by using the voltage divider theory, find the voltage here, you can find the current, okay? So what about I00 plus? What is it? I00 plus. So just touch it, just touches it. Keep in mind the electrons can travel in the almost in the speed of light. It touch it means what? What's the voltage here? So if here is grounded, okay? Let me do this. So if it touches it, what's the voltage here? Is it changing? Did anyone tell you if you connect a wire to ground, it takes like 10 seconds to get a ground signal? No, it's immediately it's 0 volts happens here. Electrons travels in the speed of light almost. It's super fast. Okay, you touch it, voltage 0, voltage 0. So if you know here's 0 volts, can you find? Oh, it's actually a wire, right? It's actually a wire. 0 volts. What's the current? Can I find the current here? So this is the wire, right? Assuming that is a wire. $100 ohms. It's basically this circuit. Can I find the current here? But you know, because this is probably will be affected by this guy. But can you find the current here first? Let's say I1. 0 volts. How? Because the circuit already formed like this. Is the resistance already confirmed? Can you find out the resistance here combined? Yeah? What is it? 100 times 300 over 400, which is 30,000 over 400, which is 20. No. 75 ohms. So if this is 75 ohms, can I find the voltage here? 25 volts times 75 over 75 plus 50 is a voltage divider equation. So you can find out Vx. If you find Vx, I1 equals Vx minus 0 volts divided by that 100 ohm resistor. I1 will be calculated. Why is that important? You need to know I1 here. You need to know I1 because after close it, like I said, the current in here is not going to change instantaneously. It's still drawing a current that way. It's a trap.
So is it equal to IL of 0 plus I?
Yeah, so I0, this equals what? I1, right? If you label this as I1, don't have space there, but I1 minus what? Yeah. Do you know IL0 plus? Yes, you did it. Do you know I1? Yes, you did it here. So this can be calculated. Okay? Be careful about this. The current here is the combination of these two currents. Okay? Study this a little bit. Watch the video, look at the notes. So I can have 2 less people visiting during office hours on Wednesday. Otherwise, there will be like a ton. 10 probably, I don't know. This is I0 plus. What about IL0 plus? IL0 plus. Oh, IL0 plus. It's not changing instantaneously, so it's equal to this, which we already did it. Why is I? Because we know VLT equals LDIT dt. So IT equals 1 over L integral of VLT dt. So why the current is not changing instantaneously? Because you are going to need an infinite of voltage to make it happen. It just have to integrate gradually to make it happen. So it's not changing instantaneously. It takes time. Okay? So the current of the inductor cannot change instantaneously. Keep that in mind. So this is always this is always valid. Okay? What is IL0 plus? Can I describe it very quick? I know it's simple, but just in case, just check if you are following. What is IL0 plus?
The discharge rate of the inductors.
It's an inductor current right after close the switch, right? What is this? It's right before you close the switch or you change the state of the switch. Any questions before we move forward? No? I0 infinity. I0 infinity is what? After a long time, so C is closing, right? We close it after a long time. What is I0? 0. Why? You have finite amount of current in here, right? It's already discharged. It discharged through where? Through the resistor, right? So the initial current stored in here after close the switch. What kind of response? It's actually established there's something affecting it. But anyway, so it's discharging, right? Discharging through the resistor and forming heat across the resistor, generating heat. So eventually all the energy here will be gone. So eventually the current here becomes 0. It's just nothing. There's no source. After 100 years, there's, oh wait, sorry, no. I0, IL. Am I asking IL or I0? I0 infinity, I0 infinity. We have another source here, so it's actually not totally 0. So what's the equivalent circuit for that case? You close it, right? And this one discharge, this one is affecting whatever. I don't care the details for now. So eventually it becomes a state that nothing is going to change anymore, DC circuits. So this becomes what? Wire, okay? What is this though? A switch. It's also a wire. So what's happening? Do I have a source here? No source, right? Do I have a source here? Yes. So it's going to pump current in here and split. Then do what? You got a wire here. Do what? Short it. Is it moving here? You got a wire here. Why not moving here? You got a resistor as well. It's just harder to do it. So don't do it. Psh, come back. So circuit becomes this. Can I find out I0 infinity?
Is he with the I1, right? Because it's not here. IL0 being IL.
Yes. It'll be the same current as this one. Yeah, because 0 volts here, right? We got 0 volts here. Right, it's the wire. 0 volts, right? Yes. Yes. Just in case, I'm drawing this circuit for you. When you are working on this homework, you'll see this circuit, this equivalent circuit, so it helps. Okay? I0 infinity. Right? What about IL infinity? IL infinity. Yeah. We just talked about that, right? It's getting shorted. So nothing. Make sense? What about ILT when for t larger than 0? ILT. What kind of response it is? ILT. Oh, it is actually natural response. I'll let you tell me why. After this is closed,
It's shorting it.
it's shorting where?
It's not interacting. Yes.
Here, gone. Why? Because this one store initial energy, right? You know, before you close it, there is some current going inside, right? You close it, what's gonna happen? That current find a way out. Okay, since there's a loop. So it's gonna come here. Okay? There's $1 million, right? But there's $1 billion here. And then come back to pick up the 1 million. Kidding, no. Just looping. Once it's done. All right. So what's the ILT though for natural response? The equation. Do you remember it? It's what? IL what? 0 what? Doesn't matter. Plus or minus, right? Times what? E to the minus t over the time constant. Yeah. So L is L given? Yes. Is R given? Yes. Do you need to combine these resistors? No, because they're not participating in that dissipation or in that discharge. Right? What is R? Tell me. 200 ohms, right? Okay. VL 0. Do you know IL 0? Here's VL, right? What's the voltage here? 0. What's the current? IL. You already calculate everything about ILs. What's VL? Is there a voltage drop at all? Yes, because it's basically L d I L t dt, right? Which is VLT. Okay? That looks interesting. VL0. VL0, which means before you close the switch, right? Before you close the switch, what's the voltage across it? It's a wire, right? Yes. So VL0 is 0 volts. So what about VL0 plus? VL0 plus. You close the switch. Close the switch. What's the voltage here? How to calculate it? You're gonna say, hey, it's this. And then you plug 0 in it, which is fine. But why not just directly use the initial current? Since you know IL0, right? Do you know so this current is also flowing through the 200 ohm resistor as well? Okay? So, what is it? VL0. It's basically the voltage here, right? Voltage here. What's the best way to do it? If you close it, what's the voltage here? Yeah. Do you know the current at 0, the IL0? Yes, we know the IL0, the initial current. Boom, drop. What's the voltage here though? It's the negative of that drop. Okay? What about VL infinity? Close it. VL infinity. Natural response. Nothing left. 0. Are guys following? Any questions by far? What about VLT for t larger than 0? VLT. VLT. When t is larger than 0. We close it. VLT is what? It's this, right? Is there another way to find it? What's the voltage here? Again, 0. What's the voltage here? 0. Do you know ILT? Yes. Can you find VLT? Just times 200 ohms and put a negative sign in front of it. Okay? Because it's just looping in the circuit. Tired? That's why this is a good problem, right? Make you sleepy. That's how a good problem looks like. The very last one in this problem, last one question, I'll let you guys go. So what about I0t when, so 4t larger than 0? What's I0t? I0t. Close it. Wait, do we have this? I0t for t larger than 0. Oh yeah. Yeah. So if you close it, is the voltage here changing? No, it's grounded, right? It's always ground. If the voltage here is not changing, is the current here changing? No. It's a constant current. Is IL here changing? Yes, it's changing over T. That's why it's called ILT. Okay? It just combines these two to find out I0T. Make sense? KCL. Okay? So already enough, right? Any questions? See you on Wednesday. Right.